With that, we're going to get started with a section 8.2. So please, whatever you're taking notes in, please have that ready. There will be some things you're going to want to add to your notes. And we're going to get started. I'm going to share my screen. All right, so here we go. We're in section 8.2, estimating a population proportion. So everything in this section will be dealing with proportions, right? P hat, P, those types of notations. Right. In today's class, we're going to learn about how to state and check the random 10% large counts conditions for constructing a confidence interval for a population proportion. Right, the 10% in large counts condition are already things we've been checking from chapter 7. Right, the 10% condition allows us to find a standard deviation. Large counts allows us to use normal calculations. Right, the randomness part now allows us to know that we have a good sample of data to use for an inference. We need to be able to determine critical values for calculating a C% confidence interval for a population proportion using a table or technology. Right? We're going to be finding critical values similar to a z-score using table A, or we can use our calculator. We need to be able to construct and interpret a confidence interval for a population proportion and be able to determine the sample size required to obtain a C% confidence interval for a population proportion with a specified margin of error. These are the things we'll be doing today. We'll see some examples in the slides, and I also have other examples prepared to do after the slides are finished, so to go through all of these things. So first, we have our conditions for estimating P. Before constructing a confidence interval, you should check some important conditions. Right? It should be random. The data come from a well-designed or random sample or randomized experiment. Right? 10% condition must be met when sampling without replacement, which is typically how we sample for the most part in most scenarios. We need to check that n, sample size, is less than or equal to 1 over n, 1 over 10 n. The big N here is the population size. And then we check the large counts condition that both NP, number of successes in our sample, and n times 1 minus p, number of failures, anything not considered a success, are at least 10. Okay. These conditions must be met for us to be able to construct a confidence interval. If one of these three things fails, we cannot construct a confidence interval. We cannot perform a proper inference using without those conditions. Can you raise your hand if you'd like a moment to write this down in your notes? Then we can use the general formula from section 8.1 to construct a confidence interval for an unknown population proportion P. Right, we have statistic plus or minus our critical value times the standard deviation of the statistic. Right, so in this case, we're using P hat. In 8.1, the critical value was like the z-score, what distance from P hat or from our population proportion do we want to be, right? Or how many standard deviations, right? So that's how we saw these in 8.1. The sample proportion P hat is the statistic we use to estimate P. When the independent condition is met, meaning knowing one outcome does not influence the other outcome, the standard deviation of the sampling distribution of P hat is, given here, we have sigma P hat equals the square root of P times 1 minus P over N. Right, this would be our standard deviation for the sampling distribution. Since we don't know what P is, meaning we can't use it in a calculation, we replace it with the sample proportion P hat. This gives us the standard error. So now it's very similar to the standard deviation. It's kind of like the standard deviation of our sample, and we call it the standard error of the sample proportion. It's the same formula. We replace P with P hat in both places. So we get square root P hat times 1 minus P hat divided by N. And this is equal to the standard error, which we can use the letters SE, capital SE for, or we can do S subscript P hat. Both work. When the standard deviation of a statistic is estimated from data, the results is called the standard error of the statistic. So we need a moment to write anything down. So how do we find the critical value for our confidence interval? Right? This guy here. If the large counts condition is met, we can use a normal curve. To find a level C confidence interval, we need to catch the central area C under the standard normal curve. So again, we have our standard normal curve. Suppose we're looking for a 95% confidence interval. So we're capturing the middle 95% of the curve, which we've done before. We have our 68, 95, 99, 7 rule. And we previously said, well, 2 standard deviations to the right or the left gives us the 95% in the middle. And that's what we have previously, right? To find 95% confidence interval, we use a critical value of 2 based on the 68, 95, 99, 7 rule. However, using table A or a calculator, we can get a more accurate critical value. Using table A, we'll get a z-score of negative 1.96 to the left and positive 1.96 to the right when we find the area of 0.025 on the interior of the table. Right, note the critical value z star is actually 1.96 for a 95% confidence interval. Z star, this guy here, is the critical value for our sample proportion. Right? Because we're not dealing with the entire population, we're not calling this critical value a z-score anymore. It is translated to z star, and z star represents the distance from our sample proportion, right? The distance, how many sample errors we are away from the sample proportion. Okay, yeah. Right. And this will always be a positive number. We will either subtract it or add it. Does anyone have any questions so far? So let's look at an example of finding a critical value. In this example, we're going to use table A to find the critical value z star for an 80% confidence interval, assuming that the large counts condition has been met, so I can use the normal curve. Since we want to capture the central 80%, the middle part here, of the standard normal distribution, we leave out 20% or 10% in each tail. We get 0.1 of the area here, 0.1 of the area on the other tail. We're going to search table A to find the point z star with area 0.1 to its left. So we're going to find 0.1 on the interior of table A. So here's the little section of table A we're going to need. We see that 0.1003 and 0.0985 are the closest values we get to 0.1. Neither of them are exactly 0.1, but these are as close as we can get. Right? 0.1003 is closer to 0.1 than 0.0985, so we're going to use that value. This leads to negative 1.2 in the left-hand z column and 0.08 in the top row of z values. which gives us the z-score of negative 1.28. We combine these two parts. So our critical value z star for an 80% confidence interval is 1.28. Notice again, it's a positive number. And we say we are negative z star equaling negative 1.28, or just z star 1.28. So that is the critical value for an 80% confidence interval. Is there anything I can clarify about this so far?
For the 0.7, 0.8, 0.9, that's the table that we use to look for the answer.
Yeah, so that's part of table A is what they have taken out here. Let me pull up the whole table. Sorry, so sorry, we don't need all this on here. That was from something I did yesterday. Don't mind this stuff. It's a lot of notation. We're not there yet. All right. Good enough. So, right, when we use table A, there's the top row of values and the left-hand column of values. The two values together give us the z-score. And so in this example, we're finding the closest entry to 0.1 that we can. And that is, where is it? Right here. Right, and so so this is the section of table that they cut out, right? They're showing us these values here, right? 0.103 is the closest to 0.1, right? And that goes to 0.08 on the top row. And negative 1.2 on the left column. When we combine these two, right, this provides me the whole number, the first decimal place. The top row gives me the second decimal place value. So this turns into negative 1.28. Did that answer your question?
Yes, it did. Thank you.
You're welcome. Okay. So yeah, they just cut out a little section of the table. So, all right. Any other questions? Anything else I can clarify? So once we find the critical value z star, our confidence interval for the population proportion P is our statistic P hat, right? Critical plus or minus critical value z star times the standard deviation of the statistic. In this case, it's the standard error, this part. So this formula produces the confidence interval, right? And it gives us an interval because we add this value and then we subtract this value from P hat, so we get two values, a lower value and a larger value, which gives us the upper and lower bound for our interval. We call this method, this is a method of inference. It's called the one sample, because we only took a single sample, z interval, because we're using z-scores, for a population proportion. Right? And this allows us to make an inference about the entire population, hence it's an inference method. When the conditions are met, a 60% confidence interval for the unknown proportion P is P hat plus or minus Z star times the square root p hat times 1 minus p hat divided by n, where z star is the critical value for the standard normal curve with c percent of its area between negative z star and positive z star. Right. This formula you're going to want to write down. You're going to want to have it available. All right. You're going to want to say what it is. Right. On your formula sheet. Right. You don't get that whole formula. Right? So you want to practice with this and understand what it is, because you will need to use it. Right? When we look at our formula sheet here, when sampling distributions, right here for proportions, it provides us the standard error formula, right? The standard error for sample statistic. It doesn't give us how to create that interval, right? This p hat plus or minus z star, blah, blah, blah. Right? So this is a formula that we're going to want to be familiar with. Okay. So we need a moment to write this down. So we have a 1 sample z interval for a population proportion. An example. So let's suppose that you took an SRS of beads from a container, a rather large container of beads that only contains red or white beads, and got 107 red beads and 144 white beads. We're going to calculate and interpret a 90% confidence interval for the proportion of red beads in the container. Mr. Mosley claims that 50% of the beads are red. We will use our interval to comment on this claim. We have a sample proportion, p hat, 107 out of 251, because 107 plus 144 is 251, and we get 0.426. Conditions were checked, supposedly in this scenario previously. We'll just run through them real quick. This is random because this is an SRS, simple random sample. The 10% condition is met because we have 251 beads total, and that's less than 10% of our massive container of beads for this scenario. And the large counts condition is met because we have 107 and 144 are both greater than 10. So our conditions are all good to go. All right. We're going to need this section of table A for a 90% confidence interval. Right? Z star is equal to 1.645. Right? And we get this because 90% leaves 10%. Right? We leave 10% out. We split that evenly between the two tails of our normal curve. That leaves 5% for each side. Okay? So we're looking for 0.05 on table A. These are the two values closest to 0.05. They're actually the same distance from 0.05. So we can't necessarily pick one or the other, so we just pick in between, which is why this Z star has an extra decimal place. Most of the Z scores we find will only have 2 decimal places from table A, because that's what it provides us. But in this case, because the difference, right, the distance from 0.5, the value at 0.05, the value I want is the same, I'm just going to go halfway between these two decimal places, which would be 0.045. So it gives me a second and third decimal place for my Z-score. So we get negative 1.645, which translates to a Z-star of 1.645. Did you guys follow that?
Yes. So how come the 1.645 doesn't have a negative like it does in the table?
So the Z star, because it's a critical value, it's what we're multiplying by. We're considering it a distance, so it's kind of like an absolute value. I just need to know what the number is. I don't care if it's positive or negative. Because what I'll do is I'll multiply it by my standard error, add and subtract it to my p hat, And so I don't need the negative sign. I could keep it theoretically, and I would end up with the same two upper and lower bounds. It would just have the sign would just be extra. It would cause an extra layer of calculation that we don't need. That's the long and short answer, I guess. Did that answer your question?
Yeah, thank you.
Okay. So here's our rule. Here's our formula here for our interval. We put in our values that we have. P hat is 0.426. Z star is 1.645. And our standard error is the square root of 0.426 times 1 minus 0.426 divided by 251. We get 0.426 plus or minus 0.051. When we subtract 0.051, we get 0.375. When we add 0.051, we get 0.477. And that creates our interval, 0.375, 0.477. This number here, right, the number we end up adding or subtracting after multiplying the critical value and standard error is considered the margin of error, which will be talked about next. Answering our question here, we are 90% confident that the interval from 3.75 or 0.375 to 0.477 captures the true proportion of red beads in the container. Since this interval gives a range of plausible values for P, and since 0.5 is not contained in the interval, we have reason to doubt the claim. I want you to take note of how this is worded here. Right? We're giving specific evidence, right? Since the interval gives us all of our plausible values, and 0.5 is not one of them, we have reason to doubt the claim. We do not have enough reason to say the claim is completely false, or that it's not true. We'd have to run more sampling to figure that out. But we have reason to doubt based on our sample. Okay, so you want to word things in that way. We're not going to say it's right or wrong yet. We're just going to say we can doubt it or we have reason to believe it. Okay. Is there anything else I can clarify on this example? Okay. So something else I want to outline here is the four-step process. All right, this has come up in other places within the textbook. And this gives us a roadmap to the way that the graders of the AP exam want you to answer questions, like free response questions. All right, we're going to use this four-step process. This is for confidence intervals. All right, we want to state what parameter do you want us to estimate? Right, population proportion, population mean, right, population standard deviation. It could be whatever the parameter is, and at what confidence level. Right, what percent confidence are we looking to achieve? We need to plan, identify the appropriate inference method. Right. In this section, we're using that one sample Z interval. We need to check conditions. Right. Random, 10% and large counts. If the conditions are met, perform calculations. Find the interval, right? Or whatever thing else they're asking you to find. Conclude, interpret your interval in the context of the problem. Right? This is important, context of the problem. Just providing the interval and saying, here's the interval, it's not enough, it's not sufficient. You need to say what it means. Right? Within the context, you must refer back to what the original context of the problem was talking about. Okay. Having all four of these parts, all four of these steps, is what the graders, the AP graders, are looking for. So we need a moment to write these down. So the next thing we talk about here is choosing the sample size. Right? In planning a study, we may want to choose a sample size that allows us to estimate a population proportion within a given margin of error. Right? Sometimes before we run our sample, we want to decide what size of sample we need for a given like confidence interval or confidence percent or margin of error, right? Because it could save us money, right? If we're actually having to pay to send people out to do this collection of data, right? Collecting too much could be spending money I don't have to spend, right? Or taking too small of a sample would mean that I have to do it again. So we want to find that sweet spot. Right? The margin of error, ME, in the confidence interval for P is ME equals Z star times the square root of P hat times 1 minus P hat over N, standard error, critical value. Right? So it's that value we're adding or subtracting to P hat is the margin of error. Z star is the standard normal critical value for the level of confidence we want. Because the margin of error involves the sample proportion P hat, and we haven't ran a sample yet, we have to guess the latter value when choosing N. There are two ways to do this. We can use a guess for P hat based on past experience or a pilot study. Maybe someone did an initial like small sample of the thing that you want to do a larger sample on, or a more comprehensive sample on. So we can use that as a guess. Or we can use P hat equaling 0.5 as the guess. The margin of error will be largest when P hat equals 0.5. So using 0.5 will guarantee a usable margin of error, right? It's going to work. It'll be the largest possible margin of error for whatever confidence interval we're dealing with, but we know it'll be good. So those are the only two options. And it's summarized here. So to determine the sample size that will yield a level C confidence interval for a population proportion P with a maximum margin of error ME, solve the following inequality for N. Z star times the square root of P hat times 1 minus P hat divided by N is less than or equal to margin of error, ME. Right, this is an inequality where P hat is a guessed value for the sample proportion. The margin of error will always be less than or equal to ME if you take the guess P hat to be 0.5. Right? So we need a moment to write this down. So now, let's do an example. So a company has received complaints about customer service. The managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some ideas of the sample size that she will be required to pay for. One critical question is the degree of satisfaction with the company's customer service measured on a 5-point scale. The president wants to estimate the proportion of P of customers who are satisfied, that is, who chose either satisfied or very satisfied, the two highest levels on the 5-point scale. She decides that she wants the estimate to be within 3%, 0.03 is a decimal, at a 95% confidence level. How large a sample is needed? Right, so here is our context. So what we're trying to solve here, our problem, is we need to determine the sample size needed to estimate P within 0.03 with 95% confidence. All right. The critical value for 95% confidence ends up being a Z star of 1.96. We found this result earlier in the presentation, right, when we looked at the 95% confidence interval and the critical value that goes along with it. We have no idea about the true proportion P of satisfied customers, so we decide to use P hat equaling 0.5 as our guess. Because the company president wants a margin of error of no more than 0.03, we need to solve the equation margin of error less than 0.03. written with our fancy notation, we get this equation, right? We have our z-score, 1.96, times standard error, square root of p hat times 1 minus p hat over n, less than or equal to 0.03. We're going to multiply both sides by square root of n and divide both sides by 0.03, and we end up with this. And square both sides. We get 1.96 over 0.03 squared times 0.5 times 0.5 is less than or equal to n. Run the left-hand side through our calculator, and we get 1067.111 is less than or equal to n, meaning the value of n must be greater than or equal to 1067.111. We're going to round up to 1,068 respondents to ensure that the margin of error is no more than 3%. We are not allowed in this scenario to round down to 1,067, even though we're closer to that value, because n cannot be smaller than the value here. 1,067 is less than 1,067.111, which means we can't use it. Right? We have to use a value greater than, and since we're dealing with people, we're going to round it up to a whole number. Is there any questions about this example? So that brings us to the end of the presentation here. All right, so now we're going to switch over and look at some other examples that I've selected from the textbook that involve multiple steps, as in some of the reflections on the self-assessment part of our FRQ. A lot of people ask for more examples, so we're going to have some more examples and more examples that are a little more complicated than the ones that we see typically in the presentation. Go. Cool. All right, so here is our context, and this context should look somewhat familiar because we saw the same context in our 8.1 practice problems last week. So Tanya wants to estimate what proportion of her school's seniors plan to attend the prom. Proportion. She interviews an SRS of 50 of the 750 seniors. In her school, and finds that 36 plan to go to the prom. We need to identify the population and parameter of interest. That's question A. All right, the population is the seniors at the high school. All right, and our parameter of interest is the proportion of those seniors that plan to go to prom. Okay. And next we need to check the conditions. Need some more space. All right, and for constructing a confidence interval for the parameter, and we have three conditions: random, 10%, and large counts. Okay. Is this random? Yes. The sample was an SRS, means it was random. Right? 10% condition. since 50 out of 750 is less than right? This is our 10% condition. That is met. And since 36 and 14 both greater than 10, the large counts condition is met. Can someone tell me, where did 36 and 14 come from?
36 is going to be the plan, the senior is the plan to go to the prom, and 14 is going to be the, I know that you subtracted 50 out of 36, and that'll be the 14.
It's right.
That don't want to go, correct?
Right, the ones that aren't planning to go. Right? And so success is the 36, failure is 14. Both of those are greater than 10. We're good on large counts. Okay. Excellent. So now we can continue. Take a little more space. All right. So now we want to construct a 90% confidence interval. For P, we need to show our method. We've got to interpret the interval in context. All right, so we're going to use the one sample Z interval for P. All right, our 90% confidence interval for P, we need to see what data we have so far, right? So we know what P hat is. And that's going to be the 36 out of 50, which is 0.72, which means we can calculate the standard error, because we also know what N is, right? So we can do this calculation ahead of time if we want. We can say 0.72 times 0.28 over 50. Because I didn't write this down, I'll put it in my calculator. We get 0.0635 approximately. Sorry, by 6. That's better. All right, so we have a standard error. All right, we need Z star. We don't have this guy yet. We need that to get our interval. So the 90% confidence interval, right, again, leaves 10% on each side, or 10% left out, 5% on each side. So again, we go and find that value closest to 0.05. And that's going to be... Where did my 0.05 go? Fine, here. Oh, so there it is. All right, so again, these are going to be my two closest values. They're actually the same distance from 0.05. So this is what we saw earlier. We get negative 1.6. And we're going to go right up in between these two and use 0.045. So we get that z is negative 1.645. So we'll have a z star of 1.645. There. Now we have everything we need. We can find our interval. Right, so we will do p hat plus or minus z star times the square root of p hat 1 minus p hat all over n, and that's going to be our 0.72 plus or minus 1.645 times 0.0635, which gives us an interval from 2 plus minus we get approximately 0.0616 to 0.824. And this is our interval. Right? But again, we're not done. Right? We must interpret this in context. All right, so now we do our final little statement here. All right. We are 90% confident that the interval from 0.616 to 0.824 captures the true proportion of seniors who plan to go to prom. All right. And so again, we find our interval. We have our last thing to do is to interpret that interval. That is, we're 90% confident that the interval from 0.616 to 0.824 captures the true proportion of seniors who plan to go to prom. Is there any questions about this example?
No, but I'm sorry, can you scroll up, please?
Yeah. Is that enough? Good.
Yes.
Okay.
Okay, there you go. Thank you.
Good. You're welcome. All right. So we're going to do our next example. All right. So we have a national opinion poll found that 44% of all American adults agree that parents should be given vouchers that are good for education in any public or private school of their choice. The result was based on a small sample. It's kind of like a pilot sample. How large an SRS is required to obtain a margin of error of 0.03 in a 99% confidence interval? Answer this question using the previous poll's results as the guessed value for p hat. All right, so again, I'm going to start by writing down what I know, what's provided, what's the given data. We know p hat is going to be guessed at 0.44. We want a 99% confidence interval, which means we can find z star. So we'll do that. N is what we're trying to find. And the margin of error is 0.03. So these are all the parts that we need. So we can go get z star, so that's what we're going to do first. With a 99% confidence interval, right? That leaves 1% to split for the tails, which gives us 0.005 that we're looking for on table A. All right. So that's what we're going to use to find z star. So we'll go back to our table A. And we're going to find 0.005, or as close as we can get to it. So here we go. These two values are as close as we can get. Once again, they're the same distance from 0.005. All right, so we're going to go in between. Use 0.075. And negative 2.5. So z-score of negative 2.575 gives me a z star of 2.575. All right, now we need to set up our inequality to solve this thing. So the inequality will be, we have z star times the square root of p hat 1 minus p hat divided by n is less than or equal to margin of error. This is the general form for the formula we're going to use. So we'll replace this all with the values we have now. So we get 2.575 times the square root of 0.44 times 0.56 divided by n less than or equal to 0.03. I'm going to break apart the square root. And this is based on the rule that if I have a square root of a fraction, a over b, this is equal to the square root of a divided by the square root of b. So I can break up my standard error into two square roots. So we're going to rewrite this as 2.575 times the square root of 0.44 times 0.56 all over the square root of n less than or equal to 0.03. I'm now going to multiply both sides by the square root of n and divide each side by 0.03. This will result in my square root of n moving to the right-hand side and the 0.03 moving to the left-hand side, so I have only numbers on one side and my variable on the other. Right, so square root of n cancels, 0.03 cancels. We now have 2.575 times the square root, 0.44 times 0.56 divided by 0.03 is less than or equal to square root of n. We gotta take the square of both sides. That gets rid of my square root over n. And we end up with n is greater than or equal to, where I have it written down, 1,841.84. Right? So we're going to round this to 1,842 and write the conclusion here. So we would need an SRS of 1,842 respondents to obtain a margin of error of 0.03 in a 90% confidence interval, and that's our conclusion. Is there any questions about this process we just went through?
How did you get 0.005?
Okay, so 0.005. Okay, let me use this color. So 1%, right? 1% is equal to 0.01 as a decimal, right? 0.01 divided by 2 is 0.005. Because again, I have 1% left over. That's not part of the central area that I'm concerned about for my confidence interval. And I have to split that evenly between the two tails of my curve. So I cut it in half, get 0.005. And 0.005 is what I can find on table A, because table A will only give me what's to the left of the left-hand side tail, right? The area to the left of that value. So that's what I find on the interior.
Okay, thank you.
You're welcome. Is there any other questions or anything else I can clarify for this part? Let's go one more part. Right. So the last part here is we have to answer the question in part A again, but this time use the conservative guess. P is equal 0.5. How much do the two sample sizes differ? I thought I deleted that extra question mark. Maybe I didn't. All right, so we're going to start by using a bit of a shortcut. All right, for this scenario, we're using p hat equals 0.5. We already know z star from above. We don't know n. We have the same margin of error. We also just did a whole lot of calculations up here that rearranged my original formula to actually solve for n. So I'm going to use that as the base for what I'm doing down here. Ultimately, I got that n is greater than or equal to z star times the square root of p times 1 minus p hat divided by the margin of error squared. So rather than doing all of that rearranging again and starting with the original, I'm going to save myself a little bit of time in calculation and just plug in all my numbers. So we get n is greater than or equal to 2.575 times the square root of 0.5 times 0.5 divided by 0.03. All of that squared. We get n is greater than or equal to, oops, I screwed up. I read my wrong result previously. One moment. That one was supposed to be 1,815.32. This one's a 1,841.84. Sorry about that. Which means we round up to 1,842. So we would need an SRS of 1,842. Which is 26 samples larger. And now we've answered question B. So anything else I can clarify? Any questions you have? So then, that's all I have planned for today. Tomorrow, we will get an opportunity to practice using these formulas and performing some of these calculations. We've got a Desmos activity to work on so that we can get a little more familiar with this stuff. And the practice problems for section 8.2 are available in Canvas along with their solutions, as well as the study guide for sections 8.1, 8.2, and 8.3. Those are all in the resources. And there's also a bunch of AP Daily videos in the resources that I have linked in Canvas for section 8.2 and 8.3 for estimating population proportions and means. We'll get to the means next week. All right. So if there's any other questions, please feel free to stick around and ask. Let me know. Otherwise, have a great rest of your day, and I will see you tomorrow.